Hello, today we're going to introduce acids and bases. So let's review really quick what a Bronsted-Lowry acid and base is. This is review from section 4.8, I think. So a Bronsted-Lowry acid is anything that donates hydrogen ions to the solution. So if you have something like hydrochloric acid, it breaks down into hydrogen ions and chlorine ions in water, so it donates those hydrogen ions to the solution. It's an acid. Okay, Bronsted-Lowry base is anything that increases the amount of hydroxide ions in the solution. But we'll get to it. So if you have something like a NaOH, that splits up into sodium ions and hydroxide ions. All right, so it increases the amount of hydroxide ions, it's a base. But this is a narrow definition. You can also have things that increase the hydroxide ion concentration by simply removing hydrogen ions from water. So another example would be ammonia. So NH3 can actually react with water, and the ammonia can steal a hydrogen ion from water, so it removes the hydrogen and becomes NH4 plus and leaves hydroxide ions. So that's why we use the Bronsted-Lowry definition, because anything that takes hydrogen ions out of the solution will leave behind hydroxide ions. And both of those are bases. Alrighty. You could also write your acid as reacting with water instead. HCl plus water reacts to form, the acid will lose the hydrogen and the base will gain the hydrogen. So that becomes H3O plus, which is hydronium, or this is essentially the same thing as hydrogen ions. It's a big thing to remember for this chapter is whenever you have an acid and it's forming those H plus ions, hydrogen ions, all of those hydrogen ions are going to attach to water in the solution. So you will always have H3O plus. So effectively, our concentration of hydrogen ions will always be equal to the concentration of hydronium ions. Sometimes we just use this one because it's simpler, quicker to write than hydronium. All right. So just be able to use both of those expressions interchangeably, the H plus versus H3O plus, they're the same. You should also be able to identify acids, bases, and then conjugate acids and bases. So if the ammonia here is a base, the water must be acting as an acid. And when a base gains a hydrogen, it becomes a conjugate acid. When an acid loses its hydrogen, it becomes a conjugate base. So this is a conjugate acid-base pair, and this is a conjugate acid-base pair. In our second example, this is acting as an acid, so the water is acting as a base. And when the acid loses its hydrogen, it becomes a conjugate base, and when the base gains a hydrogen, it becomes a conjugate acid. So make sure you're able to identify conjugate acid-base pairs. You should also notice that water can act as either an acid or a base, depending on the scenario. We call things that can act as an acid or a base amphoteric. We also say sometimes, sorry, I missed an M, amphoteric. We also call them amphiprotic sometimes. But either of those words means it can act as an acid or a base. Let's also quickly review your strong acids and strong bases. Remember that strong in this context means that it completely dissociates into ions. So your strong acids are HCl, HBr, and HI, HClO3, HClO4, and then HNO3 and H2SO4. So those are your 7 strong acids, and then your strong bases. You need to know we have LiOH, NaOH, KOH, RbOH, CSOH, and then calcium CaOH2, SrOH2, and BaOH2. And I write it like this because it follows the pattern on the periodic table. 5 of them from your group 1 metals and 3 of them from your group 2 metals. So make sure that you know those 7 strong acids and 8 strong bases. they behave differently than the weak acids and bases. If it's not on this list, then it must be weak. And you definitely need to know them. Okay, so let's talk really quick about the pH and pOH scales. So when you see P, and we always write lowercase p, pH versus pOH. Lowercase p means that you're taking the negative log of something. So in this case, you're taking the negative log of H, and we know that it's hydrogen, so it's H+, and then pOH would be negative log of the OH. So lowercase p means negative log. So based on your hydrogen ion concentration, that's how you're going to get pH. And it's a negative logarithmic scale. So what that means is it's based on the number of decimal places in your hydrogen ion concentration. So let me write it over here. If I have a hydrogen ion concentration is 0.1, my pH is 1. If my hydrogen concentration is 0.01, my pH is 2. My hydrogen ion concentration is 0.001, my pH is 3. I'm starting to see the pattern now that it's the number of decimal places, and it will give you the pH value. So you'll have a pH scale form with 7 in the middle, just about 14 at the top and 0 at the bottom. And then 7 is going to be neutral for the most part. We'll talk about that in a minute. Neutral. And then when it's below 7, it's more acidic. Okay, you have more of the hydrogen ions present. And a lot of people struggle with that, but it's because lower values are more acidic because it has less decimal places. So it has a larger concentration. And then the greater it is, it will be a base. So it will have more decimal places in the hydrogen ion concentration, so less acidic, more basic. You can also find the pOH scale. So hydroxide ion will tell us about the amount of base, essentially, in the solution. So your pH scale winds up being 7 is also neutral most of the time. And then above 7 on the pOH scale is an acid. So it's flipped. Below 7 on the pH scale is a base. Right? So make sure that you know those scales. So if a question says something like, the pH winds up being 2.5, you know that's acidic. If the pH winds up being 8.9, you know that's basic. And then the reverse as well. If you know that the pOH is 9.7, that's an acid. If the pOH is 3.2, then you know that's a base. So be really familiar with your pH and pOH scales. So you might have to convert between pH, pOH, hydrogen ion concentration, and hydroxide ion concentration. So there's a really convenient kind of box model that we use, pH and pOH. And then all of these values that I'm going to give you are for 25 degrees Celsius. And we're going to talk about that later in this presentation, about how it will change at different temperatures. But for the most part, we're using 25 degrees Celsius. So if you want to convert between pH and pOH at that temperature, you'll use this equation, pH plus pOH equals 14. So you can just subtract to find the other thing. Okay, and then when you want to, let's see, we have hydrogen ion concentration. We already talked about if you have hydrogen ion concentration and you want to find the pH, we know that's the negative log of the hydrogen ion concentration. We also talked about hydroxide ion concentration to pOH. That's the negative log of the OH concentration. Okay. Now, so the opposite of a logarithm is an exponential notation. So these are all log-based 10s. Okay, it's just we don't typically write them because that's the normal logarithm. So if I were to rearrange that for H+, you would get a 10 to the negative pH. Okay, I'll show you really quick. pH equals negative log of the H+. want to move the negative sign over first. Negative pH equals log base 10 of H plus. And then this is the base, this is the exponent, 10 to the negative pH equals H plus. Okay, so 10 to the negative pH is how you get from pH to the hydrogen ion concentration. And so the same is true for POH. You'll do 10 to the negative POH to go backwards and find the OH concentration. And then our last little calculation here, you might have to convert between the hydrogen ions and the hydroxide ions in a solution. And so that calculation at 25 degrees Celsius is 1 times 10 to the negative 14 is equal to the product of hydrogen ions times hydroxide ions. And that's because, remember, the lowercase p is equal to negative log. And I kind of wrote this one backwards, but here, let me write it the correct way around. Hydrogen times hydroxide equals 1 times 10 to the negative 14. If you were to take the negative log of this whole expression, then you would get this simplified version up here. I don't really want to do that out for you guys now, but it winds up being the same thing. It's just whether you're using the negative log versions or whether you're using just the straight up molarity versions. So really be familiar with how you can convert between any of those 4 different things. Okay, so now let's talk a little bit more about water. Water, especially, we said it was amphiprotic or amphoteric. Water can do what's called autoionize, which is where it splits up into hydrogen ions and hydroxide ions. So liquid water splits up into hydrogen ions and hydroxide ions. Now, liquid water only does this to a very, very, very small extent. Okay, so if we were to write a K expression for this, we would get the hydrogen ions times the hydroxide ions. And we would not include the liquid water because it's a liquid. So this is what we call KW because it's for water, for pure water. It's hydrogen and hydroxide. Now, the vast majority of our acid and base are very, very low concentrations. So that means they're mostly water solutions, which is super helpful for us because we can use KW to convert between H plus and OH negative. And at 25 degrees Celsius, KW is 1 times 10 to the negative 14, which we talked about on the previous slide. So that's kind of where that comes from. Now, if you have a pure water solution, pure water, only water, that means your water is equally breaking up into hydrogens and hydroxides. So hydrogen and hydroxide are equal in pure water, and that's how we define a neutral solution. That is the real definition there. Hydrogens are equal to hydroxides. Okay, and if they're equal, we can say that 1 times 10 to the negative 14 is equal to x squared, or x equals 1 times 10 to the negative 7. And that's our hydrogen ion concentration and our hydroxide concentration. And if I take the negative log of this number, I get that the pH is 7. I also get that the POH is 7. So when KW is 10 to the negative 14, my pH and POH are both 7, which makes sense because they're equal. All right. So that indicates that neutral solution. Now, it doesn't have to be a pure water solution. You can still use this equation because if there's extra hydrogens in the solution, they're going to bind to water to form hydronium, and other things are going to happen. You can still use this, but you wind up with a different definition for an acid and a base. An acid solution is going to have more hydrogens than hydroxides, and a base solution will have less hydrogens than hydroxides. Now remember, we can substitute hydronium, H3O plus, in for any of these H pluses. It's the same thing in water solutions. Alrighty. Because those hydrogens don't like to float around on their own, they like to bind up with water. So if you were to write this initial equation a little bit more accurately, you would wind up writing water plus another water molecule leads to H3O plus and hydroxide. So where this is the acid and base, the acid transfers a hydrogen and becomes the conjugate base, and then the base gains a hydrogen and forms the conjugate acid. So that's one of your pairs, and that's your other pair. This one is just a simplified version. Okay, so all of the ones that I've done so far have been at 25 degrees Celsius, and I will say the vast majority of the questions you will see in this unit will be at 25 degrees Celsius. However, they could ask you about how Kw changes and how the pH-POH changes when the temperature changes. So let's say you have a higher temperature. Okay, at higher temperatures, more of the water will dissociate. More of it will break down into those hydrogen ions and hydroxide ions. All right, so you're going to have an increased concentration at a higher temperature. Okay, so Kw is equal to H plus times OH negative. That's still true because we don't include the liquid water. But both of these are increasing. Well, that's going to increase your value of Kw. Remember from Unit 7, the only time our value of K changes is when the temperature changes. So, at a higher temperature, we're going to have a larger value of Kw. So let me just make up a number. Let's say at some higher temperature, our K is equal to 1 times 10 to the negative 13 instead. Oh, let's do 12, make the math easy. Okay. So at some increased temperature, we have this value for Kw. Well, if you have a pure water solution, pure water, I know that my hydrogens and hydroxides are equal. So I know that we can do x squared, and then we can solve x is 1 times 10 to the negative 6. And that is equal to both my hydrogen ion concentration and my hydroxide ion concentration. Oops, equals, there we go. And if I take the negative log of this number, I get that the pH is equal to 6. Well, it's also the OH value, so if I take the negative log, I get the POH is also equal to 6. So that means at whatever this temperature is, neutral is actually at a pH and POH of 6. So that's why I said this is all temperature dependent. So you need to be careful. The best definition of a neutral solution is when your H and OH are equal, or your hydronium and your hydroxide are equal, because the specific pH or POH could change at different temperatures. But for the most part, we're going to do 25 degrees Celsius, where the pH of 7 is neutral. Just be aware of how that changes. Now, the reverse would also be true. If you decrease the temperature, you'll have a smaller value of K, so you'll have smaller concentrations of hydrogen and hydroxide, and your pH and POH would be larger at a lower temperature, even though it's still neutral. Okay, let's do some examples of this. We'll do some simple calculations first. What is the molarity of H3O plus in a solution of pH equals 2.876? So you would use the equation 10 to the negative pH equals H plus or H3O plus. So you'd plug in 10 to the negative 2.876. And when you're doing logarithms, or rather exponential, you use however many decimal places are in that exponent becomes the number of sig figs in your answer. So you do 10 to the negative 2.876, and you get 0.00133 molar. Okay. And we know that that's an acid solution because the pH is below 7. And they didn't tell us the temperature, so we're just assuming it's all at 25 degrees, which you can do. All right, so 3 sig figs there. Now, for the second one, what is the molarity of OH in a solution of pH of 8.90? Okay, so OH. First thing you want to do is subtract from 14 to give us that the POH is equal to 5.1. And then you will do 10 to the negative POH, or 10 to the negative 5.1, will give us a base concentration, or an OH concentration, of 7.9 times 10 to the negative 6 molar OH. Okay, and again, we had 2 decimal places in our original pH, so 2 sig figs in our answer. Now for the last one, what is the OH concentration in the solution with H3O+? Now, you can do this a couple different ways, but we know that the H3O+ times the hydroxide ion concentration equals 1 times 10 to the negative 14. We can plug in here. And then you can divide both sides by the 3.76 times 10 to the negative 5 to get OH by itself. And when you divide, you get 2.66 times 10 to the negative 10th molar. Okay. Now this first example, like we said, was an acid because the pH is below 7. This one is a base, pH is above 7. Now in this case, in the third example, we can compare the 3.76 times 10 to the negative 5th compared with the hydroxide, 10 to the negative 10th. So our hydrogens are much greater than our hydroxides. And so that's how we know this last one is an acid. Now this last example, they tell us at 35 degrees Celsius, the Kw of pure water, that's important, so it's neutral, 2.09 times 10 to the negative 14th. What is the pH of water at this temperature? You should always write the K expression when we use the H3O+ version, but you could put in the H+ if you want. 2.09 times 10 to the negative 14. I'm going to plug in x squared. We know it's pure water, so hydronium and hydroxide are equal. And then you square root both sides. And you'll get that the concentration, or x, is equal to 1.45 times 10 to the negative 7th. And it's going to be the same for both of those things. Oops. And if you take the negative log of this number, you get that the pH is equal to 6.84. 6.40, I believe, if you're using proper sig figs. Now, even though that's less than 7, it's still neutral because they tell you it's pure water, and we know that the hydroniums and hydroxides are equal. It's just that the actual pH point for neutral is lower at that higher temperature.